Hello, lovely people. Today I will be telling you how I'm gonna measure all of those mid-ranges. So this video is needed just because I do know that in the past few months or so, I have quite a lot of new people joining my channel that don't really know how I do everything. And just for fairness, because if some speaker, especially if it's going to be a high-end speaker, expensive speaker that is not going to perform as everybody expected, obviously they're going to blame me and all my testing equipment on what I'm doing. So you saw the video that I did about this baffle, how I came up with this baffle, how I made it, and now I'm just gonna show you. It's fully finished. So the ring is inside. As I mentioned, everything is flush. From the other side, I add these kind of washers. I'm just gonna show you. Just like that. So this ring is kind of pulled out and it's gonna be squashed and it's not moving anywhere. So everything is super, super tight. Now, I literally can take this by the magnet and lift the whole board and nothing is moving, nothing is flexing, everything is very, very sturdy. So the mounting, there's no issue with the mounting. Now what I want to show you is the actual testing equipment, what I'm going to be using for the signal and everything else. So now I connected the Quantasylum just because I want to show you the cleanliness of the signal that is going into the speaker. Because if I'm going to have high distortion on some speakers, people are going to say, oh, your equipment is very dirty, it's not clean, and the equipment is introducing the distortion into the speaker. So what I have here is I have a linear power supply, which is not switching, so it doesn't introduce any noise or hum into the amplifier or anything. It is set for about 13.2 volts, where amplifiers perform optimally. Now, for the signal, I will be measuring with a laptop. So the laptop is going USB into SMSL. So it's not a DAC, it's a digital to digital converter. So it converts USB into optical. The optical is going into my DSP because I need something that I could adjust crossover, because if I'm gonna test small 2-inch mid-ranges, I cannot send a full range signal to it, so we need to adjust the crossover. So the crossover is gonna be adjusted on the Alpine DSP app, which is here, channel 1. So at the moment it's set link with Riley, 250 Hertz, 24 dB. Everything is in the EQ tab, channel 1, everything is flat. There's no EQ applied. All the gains lie halfway. Channel gain is set at 0, so nothing is boosted excessively or anything. So the signal is going to the DSP, optical. Then it goes from the DSP into the amplifier. Now, I chose this amplifier because this is an old school Alpine V12 MRV F305, and this is the cleanest low power amplifier that I have. It is the most clean. It's even cleaner than the one that I have in my car. And I have set on the settings everything flat, and I did set the gains, which is here, is set to nominal gain instead of 4 volts. So nominal gain, it kind of bypasses a lot of circuitry inside and it gives you a much cleaner signal. So there's no crossovers, no nothing applied. I'm going to show you the frequency response and everything. So how clean it is. I connected the Quantasylum audio analyzer to the amplifier output. So now I'm going to show you the electrical signal. And this is with a load. That load is the speaker. So speaker is connected from the amplifier. I'm going to be using REW for measurements. So this is the REW generator. And I set it up. So do excuse me for the tone because it's going to be playing. If I'm going to play the generator, 1 kilohertz, you can hear the loud beep. And this analyzer is showing me the 1 kilohertz tone and the cleanliness of it. So THD plus noise is, I just stopped the noise because it's very annoying. So THD plus noise is 0.003%. THD itself, 0.002%. So you can see that is super, super low. The highest harmonics, which are here, the second and third. So this is electrical. This is the amplifier and the DSP combination. It's not the speaker, yeah? So these, I have a second harmonic at minus 95 dB and third harmonic at minus 90 dB. So this is a super clean signal. No speaker can reproduce this. So now we know that the equipment does not introduce anything. In regards to the level, if I'm gonna have something like this, I can check it. So it shows me that it's 1 watt output and it's about 2 volts on the speaker outputs. And with this, I can check kind of the sensitivity of the speaker. So if I'm gonna play the tone again, and I'm gonna go here, I have a dB meter, if I'm gonna enable it. So this is distance of 1 meter until the front. About 90, 84, 84, 85, I'm gonna stop it. Yeah. So for example, this 1 watt, 1 meter gives me about 85, 86 decibels sensitivity for the speaker. So all of this is just for you, the viewer, to prove that all my signal chain is super clean and it doesn't introduce anything. Now I'm gonna show you the electrical frequency response. In order to do that, I'm gonna be going to noise and white noise. So I will play the white noise. Ooh. It is very loud. So what I'm gonna do, because I put 30 averages, just to average it so you can see it a bit better, I'm gonna reset. Now I'm gonna play it, it's gonna be loud, but I'm gonna wait for 30 averages to come up and then I'm gonna stop the measurement. So let's do this. So it is electrical, but because you can see the noise on the top end, yeah, I think that's fine. Yeah, that's fine. I'm gonna stop it. Okay, so this is electrical frequency response that coming from the laptop, through the DSP, through the amplifier, and going into the speaker. This is not the speakers. So you can see this is the crossover that is applied in the DSP, which is set at, as I mentioned, 250 hertz. And I can zoom in on this, just like that, just to show you. There we go. A little bit back. There we go. So this is 2 decibels. Let's increase it even more, like that. So 1 decibel, five of these grids is 1 decibel. So 0.2 decibels. And you can see, like, from here where the crossover goes, it's all the way flat. There's absolutely no issues with the frequency response. The electrical frequency response is as flat as it can be, as flat as possible. So now we know that the measurement signal is flat and is clean. Now I'm gonna close this and we're gonna go to REW and I'm gonna show you how I'm gonna do my measurements and what kind of measurements are we gonna perform. I repositioned the baffle a little bit into the middle of the room. I'm not sure if I'm gonna keep it in exactly the same place. Maybe I'm gonna put it somewhere here. I'm not sure. I'm gonna need to experiment. But the general layout is something like this. So all the equipment is in the back here. I have a measure microphone, which I will be using, which is a UMIC 1. It is positioned at the same height as the speaker, and from the front until here, until the tip, we have 100 centimeters, which is there, which is exactly with the tip. So basically 1 meter away from the speaker. This is pretty much straightforward. Now, let me show you all the settings and everything in the laptop. So first of all, if I'm gonna go to sound settings in Windows, we have the SMSL master volume is 100%, and the microphone volume is at 70. So just know to max out and to have enough level. Then if I'm gonna go to preferences, in the calibration files, I have UMIC calibration loaded, which is a non-90 degree, the normal one on axis. Then in the analysis, I set, because these are gonna be gated sweeps. If you're not sure what that is, read about it. So basically it tries to eliminate all the reflections coming from all over the place and keeps only everything that's in 1 meter. So I set it to 3 milliseconds right there. And here in the settings, we have Java drivers, 48 kilohertz, because the microphone works only at 48K. And we have the SMSL as output and the UMIC as input. Now, if I'm gonna go to the measure tab, because I will be performing only the sweeps. Sweeps, the length of the sweep doesn't really matter, so it's about 5 seconds on 256K. Now, the level, I will be playing with the level in the DSP settings and in here, because some of the drivers are 8 ohm, so they will need a bit more power. Because what I wanna do is, all the measures that I'm trying to do, I'm gonna do them at 90 decibels at 1 meter. So I have this, which shows, if I'm gonna stop talking, it's about 30 decibels of ambient room noise. And if I'm gonna click here, which is check levels, it basically checks the level of the microphone if it's okay or not. So if I'm gonna click on this and I'm gonna show you that, you can see it showed 90 decibels. So with these settings, I'm getting 90 decibels. Why 90 decibels? Because I think it's a good level where the speakers are very loud, but they're not pushed to the ultimate limit. Because if you add another one, in the car you have two, so plus 6 dB, 96 decibels is a very good SQ volume, even if you're listening loud. So I think 96 decibels for two speakers is a very good level. So we're gonna keep it at 90 dB. And then I'm just gonna do a sweep. So if I'm gonna click start, oh, the sweep, I'm gonna do it from 50 hertz to 24K. So from 50, because I wanna see what's happening down below with the distortion especially, but there's no need to play down to 30 or 20. So we're just a bit shorter measurements. So let's do one measurement. Okay, so you can see one measurement. In the SPL tab, we have this, which is a frequency response. So from this, we can see this dip, I guarantee is going to be caused because of that edge diffraction. So it's going to be in all the speakers and all the measurements, so we can disregard it. Because the most thing for us, the most important thing is going to be the top end and all of this stuff. The lower end, the roll-off, depending on the crossover frequency. What I'm going to do, I'm going to measure this near field. I'm going to show you how to do that. We're going to measure near field, and we're going to combine the two measurements to have one kind of full range measurement. So when you do this sweep, we're going to be checking the frequency response on axis. So I will be checking off axis as well. However, I'm going to be doing only one off axis measurement. So it's going to be 45 degrees or 60. I haven't decided yet. But I'm not going to do like increments a lot because there's 22 drivers in the box. It's going to take me ages. So only one. I'm going to leave some sticky tape on the floor so I would know where the tripod stand. So I'm going to put it there, and then I'm going to move it to the side about 45 degree. I'm going to measure off axis. So going to be two measurements only, and we're going to see where it kind of rolls off. Now, if I'm going to go with this sweep measurement into this distortion tab, the distortion tab shows me the distortion. So THD, second harmonic and third harmonic. Now, this measurement was taken with a crossover frequency of 200 hertz. So for this mid-range is way too low. And we can see this by the rising distortion in the bottom end. I kind of thought how to make it fair for all the drivers and what crossover frequency to choose, because we have very, very different ones. For example, this one is a barely 2-inch with little X max, and then you have something like this. It's not fair to have all the drivers on the same crossover frequency. So what I'm gonna do is I'm gonna play with this, and with every individual driver, I'm gonna choose an individual crossover frequency that makes the distortion look flat. So it's not gonna be rising. So we will kind of decide and know, according to the measurements, what is the lowest crossover frequency for every individual drivers, and within the measurements I'm gonna put the number here where that driver was crossed. So for example, this 200 hertz is way too low, so let's make another one at let's say 350. There we go, 350. Let's make a very quick second sweep and see what happens. Okay, and now you can see the distortion is under control at the bottom end. So if I'm gonna be flipping between like these two, yeah, you can see that the difference is huge. So for this specific driver, something about 350, maybe 320 could be a bit lower, but something about 350 is a good crossover. Now, if I'm gonna take a bigger driver, for example, the Steg 4-inch, obviously 350 is not going to be good, so it will need a much lower crossover. And that's the whole point, that it's not fair to compare the drivers on the same crossover frequency because the capabilities are not the same. So based on the distortion and the crossover frequency, we will know and we will learn which drivers are more capable compared to the others. And obviously we're going to have the distortion level. So we're going to analyze this in a future video, because now in this one, again, I just want to show you how I perform the measurements, what kind of measurements. And in the next one, we're going to go through all the data, because it's going to take, I don't want to make a 2-hour long video. So distortion is first. Obviously, now frequency response. So frequency response is first. We're going to analyze this. Distortion is second. We're going to analyze that. And the third one, what some people ask, and I want to have a look at as well, is a waterfall graph. So waterfall graph is going to show us if the driver is, for example, ringing somewhere. So this, for example, to me, it looks kind of okay. There's no like stuff coming out of it. The only one that I can see is something maybe here. Like if you can see this one, it kind of, but it's again, it's what, 250 hertz. So it's kind of in the crossover already. So I'm not going to call this ringing, but this graph, I think, is going to show us if any of the drivers have like severe problems. If one frequency rings, maybe it's like a basket or something, maybe it's, I don't know, something, but this will show like major issues. I don't think we're going to see anything on this, but a lot of people ask, so I'm going to include this graph as well. This spectrogram here, it shows kind of the same thing. It's just you will have these extended. So I don't know. I think we're going to use this waterfall instead of that. So the near field looks something like this. It's extremely close to the cone, as close as you can. I'm not sure if the grill is going to affect anything, but just for you to show, I'm going to leave it as it is. So near field. So with this near field, what we'll have to do is we have to change one thing. So if I'm going to go to preferences, I'm going to show you why. In the analysis, I'm going to change the width, which is the gating, from 3 milliseconds to about 17 milliseconds. And I'm going to show you why. So enter, let's close this, and let's make us another sweep. However, this time I'm gonna turn down it down to -40, because the distance is very low. I don't want to overload the microphone, so it needs to be very quiet. So I have to shut up as well. Okay, cool. So we have the measurement, and now you see that we have this measurement. And now we can see how everything rolls off at the bottom end. So with the near field measurements, what I'm going to do, I'm going to make a measurement with the crossover, how it is applied like now at 350 hertz. And then I'm going to make another measurement with no crossover applied, because on such low power, we don't care about the distortion, but we care how the actual driver performs with nothing, like raw. So let's do another one with no crossover applied. There we go. And now you can see that the two of these measurements are very different. And I wonder why. Could it be because of the Q of the driver? Because this driver has a very high Q over 1, maybe? And from this, we can see basically everything that we want to see. We see the actual natural peak, or whatever roll off is going to be. We see everything down to about 60 hertz, and there where this gating comes into play. So if you see, this is set at 17 milliseconds. If I'm going to be lowering down, you can see the frequency response is down to 200 hertz, down to 300 and etc. So it's exactly the same if I'm going to choose this one, which was the measurement of the from 1 meter away. So if I'm going to increase the gating, you can see all of these nasty things. These are the reflections that are coming in from the sides and from the ceiling and from everywhere. If I'm going to increase the gating to, for example, this is 8.6 milliseconds, we have all of this. So what I'm trying to do, I'm trying to eliminate all the reflections, and I'm closing down the gating, make it smaller, smaller, and smaller until all the reflections disappear. So see, all the reflections are gone, and I have 3.6, so 3 milliseconds. So 3 milliseconds work fine if I want to analyze the frequency response without any reflections. However, for this one, we need the gating to be quite big just to see down to 60 hertz or whatever. So this is, you see, something 18, 17, something like 17 milliseconds gating for the frequency response go down all the way to 60 hertz. Now, when we have these measurements, I will have to disregard this one and enable this. So with these two measurements, we have a kind of simulated full range response of the driver. We can see that they match somewhere here. Here we have some issues maybe with the surround or something, but this is basically all the stuff that the environment adds acoustically, but we as well see all the breakups and everything else. So with this, we need to merge these two graphs to have one graph that encompasses kind of the whole frequency response. And I'm going to be doing this in this way. So since I have two of these graphs, I'm going to go to Actions, Trace Arithmetic, and then I'm going to select these two graphs, which is graph number 2 is the one far field, and graph number 4 is the one that is near field with everything, without the crossover and everything. And here in all of these options, I'm going to choose merge B to A. Now we have to choose the frequency at which the merging is going to happen. So I could choose something like here or maybe here. So I don't know. Let's try something like 500 hertz. So 500 hertz, we're going to tick blend and we're going to generate a graph. And it generated a graph such as this. So I'm going to remove this one and I'm going to remove this one. And basically I have one single graph that encompasses the near field response and far field response, and it shows me everything. So this is going to show me the Q of the driver, the natural roll off as it is, and all the peaks and everything that is from the far fields. So this I'm going to do with every single driver on axis. So this is the plan, and now it's gonna take me a while to go through all of them. So just to recap, I'm gonna be measuring a frequency response on axis and 45 or 60 degree off axis from a distance of 1 meter at a loudness level of 90 decibels. My equipment is super clean and is super flat, so the only thing that we will be measuring is the actual speaker. After all the measurements are going to be complete, we will be looking at the total frequency response of the driver, the distortion, and the waterfall graph. We're going to be determining the optimal crossover points for each individual driver, and we're going to see how they actually perform. After I publish this video, if you have any comments, if you have any suggestions, how we can make this fairer or better, or if you don't agree with something, please comment below, because it will take me at least a week or probably more to do these measurements, to actually perform the measurements. So I will have time to adjust or change something, because I want this to be fair, and I don't want anyone to say anything that I did something wrong with it, because some of these drivers are super, super expensive, and I really don't want to mess it up, because I think all of you deserve the actual data verified by third party and not something in the data sheet. So this is it for this video, and I'm gonna start measuring everything. So thank you very much for watching, guys, and I will see you in the next one.